Hello friends, I welcome you in lecture number 12 on residues. In this lecture we will discuss one example on Cauchy's residue theorem which was asked in summer 2020 exam of Gujarat Technological University. So let's try to solve this problem. We are asked to evaluate this complex integral e raised to 2z over z plus 1 cube using Cauchy's residue theorem, where this C is the ellipse represented by this equation 4x square plus 9y square equal to 16, and it is taken in counterclockwise direction. So first we write down the given function and we find out the points at which given function is not analytic. So suppose given function is denoted by f of z, which is e raised to 2z over z plus 1 cube, and this function is division of two analytic functions. We know that e raised to 2z is analytic everywhere, and this z plus 1 cube is also analytic everywhere. So f of z will fail to become analytic at those points for which this denominator is 0. So f of z is not analytic at those points for which z plus 1 cube is 0. That means z plus 1 is 0. That means z is minus 1. So z equal to minus 1 is the only point at which f of z is not analytic. So f of z is analytic everywhere except z equal to minus 1. So we can say that f of z has isolated singular point at z equal to minus 1, or isolated singularity at z equal to minus 1. Now we have to check whether this z equal to minus 1 is inside the given contour or outside the given contour. So now we focus on the given curve. Given curve is the ellipse which is given by 4x square plus 9y square equal to 16. So without sketching the ellipse we can decide whether z equal to minus 1 is inside the ellipse or not. For that we find out real and imaginary parts of z equal to minus 1. Z equal to minus 1 can be rewritten as minus 1 plus 0I, or as a order pair we can rewrite z equal to minus 1 as order pair minus 1 0. So if we compare with order pair xy, we have x equal to minus 1 and y equal to 0. So we substitute x equal to minus 1 and y equal to 0 in the left hand side of this equation. So at x equal to minus 1 and z equal to 0, y equal to 0, we have x is minus 1, y is 0. So 4 into minus 1 square, that is 4, and this is less than 16. So from this we can say that this point z equal to minus 1 must be inside the ellipse. And if we don't want to check in this way, we can convert our equation of ellipse in standard form. So for that we can rewrite this equation by dividing whole equation by right hand side, which is 16. So we rewrite, or we divide whole equation by 16. So we have 4x square by 16 plus 9y square by 16 equal to 1. So here 4 will cancel out. We have x square by 4 plus, and this we rewrite as y square divided by 16 by 9 equal to 1. So this we can again rewrite as x square over 2 square plus y square over 3 by 2 whole square equal to 1. So this is the standard form of ellipse. If we compare with this standard form, x square over a square plus y square over b square equal to 1, we have a equal to 2 and b equal to 4 by 3. 4 by 3 means 1.2 or something, approximately 1.2. So a is greater than b, So we can sketch this ellipse. On x-axis we have to go up to 2, and on y-axis we have to go up to 1.2 approximately. So we can roughly sketch the ellipse in this way. Suppose this is the ellipse, so that this is going to be 2, this is 1, 0, -1, -2, and this is approximately 1.2 or 4/3. This is -4/3. So this is the given ellipse. Now we have to check whether z equal to -1, which is the singularity of f of z, is inside or outside this ellipse. So it is obvious that z equal to -1 lies inside the ellipse, and f of z is analytic everywhere except z equal to -1. That means f of z is analytic everywhere inside and on the ellipse except only one point, z equal to -1. So hypothesis is satisfied. F of z is analytic everywhere inside and on C except z equal to -1, which lies inside C. So hypothesis of Cauchy's residue theorem is satisfied. So we can apply Cauchy's residue theorem to find out integral of f of z along this ellipse. So for that we have to calculate residue of f of z at z equal to -1. So first we find out residue of f of z at z equal to -1. Now f of z is e raised to 2z over z plus 1 cube, or this we can rewrite as phi of z over z minus -1 to the power 3, where phi of z equal to e raised to 2z. This is analytic function, so it is obviously analytic at z equal to -1, and value of this function at z equal to -1 is e raised to -2, which is non-zero. So f of z is written as phi of z over z minus -1 cube, where phi of z is analytic at z equal to -1 and phi of -1 is non-zero. So therefore we can say that z equal to -1 is a pole of order 3, because here power of z minus -1 is 3. So therefore f of z has a pole of order 3 at z equal to -1, and we are interested in the residue at this pole. So residue of f of z at z equal to -1 will be equal to second derivative of function phi at z equal to -1 divided by 2 factorial. So now we calculate second derivative of phi at z equal to -1. Phi of z is exponential function e raised to 2z. So if we differentiate with respect to z, derivative of e raised to 2z is e raised to 2z into derivative of 2z, which is 2, so that we write here. So that is by chain rule, and then we again differentiate to obtain second derivative. So 2 as it is e raised to 2z into derivative of 2z, which is 2. So this gives us second derivative of phi equal to 4 times e raised to 2z, and we are interested in the second derivative at z equal to -1. So we have 4 times e raised to -2, or 4 divided by e square. So we substitute this value in this equation and we will obtain residue of f of z. This is going to be phi double dash -1 divided by 2 factorial, that is 2. So therefore residue of f of z at z equal to minus 1 equal to 1 by 2 into phi double dash 1 minus 1, that is 1 by 2 phi double dash minus 1 is 4 divided by e square, that is 2 divided by e square. So this is the residue of given function f of z at z equal to minus 1, 2 divided by e square, which we denote by say capital B. Now we can apply Cauchy's residue theorem. So by Cauchy's residue theorem, integral of f of z along given ellipse equal to 2 pi I times sum of residues of f of z at isolated singularities inside C, and here there is only one isolated singularity inside the ellipse, and residue at this point is denoted by B. So we have 2 pi I times B, and we substitute value of B, which is 2 divided by e square. So this is going to be 4 pi I divided by e square. So therefore we have obtained the integral of function e raised to 2z over z plus 1 cube along the given ellipse, and which is 4 pi I divided by e square. So in this way we can easily find out sum of the complex integrals using Cauchy's residue theorem, provided our function is analytic everywhere inside and on a given simple closed contour except finite number of points, and we can decide whether the isolated singular point is inside or outside C using the equation of given curve or by sketching the given curve. Okay, so that we have shown in both the cases. We can conclude that z equal to minus 1 lies inside C. So this is all about today's session. I hope you like it. Thank you very much.